All right, so next up, we're going to take a look at the properties of waves. So let me just draw a wave here. So a straight line for reference, and then a wave, right? A wave. So there's two main properties of a wave. The first is the length from peak to peak, and this is known as the wavelength. And it gets the symbol lambda, lambda. So it's the distance between peaks. That's the first property of a wave. And then the second property of the wave is the amplitude. And so the amplitude is the height of a wave. So those are the two main properties of a wave that determine what kind of thing it is here, right? And what we're really talking about here is light. So we're going to focus our discussion on a wave of light. So let's take a look at first at amplitude. And so that's the height of the wave. And what amplitude determines is the intensity of the light. So let's draw two waves with different amplitudes, but the same wavelength. So something like this versus something like this, right? You can see in both of these, they have the same wavelength, but different amplitudes. And so amplitude determines the intensity, and since we're talking about light here, we're talking about the intensity of light. So this would be something that's dim, and then this would be something that's bright. So the intensity of the light. So I got a picture of this little light bulbs here. Line them up, right? And so the top picture would be a picture of a wave that's dim, and then the bottom is a picture of a wave that's bright. So amplitude just determines intensity. Let's take a look at wavelength. So wavelength determines the color or the type of light. So let's take a look at two examples, and we'll have the amplitude be about the same, but the wavelength different, right? So something like that, not the best drawn picture, versus something like this, right? The height of the wave is approximately the same, not a perfect artist, it's a little bit different, but it's approximately the same. What's different here is the wavelength. So this one's got a long wavelength, and this one's got a short wavelength. And so we say that long wavelength is low energy and short wavelength is high energy. And this kind of makes sense. If you think about a wave, if you have a long wavelength, only one wave is hitting you at a time. It's not too bad. You can kind of recover in between waves. But these high energy waves, they keep coming at you. So they keep hitting you again and again and again. And so those are kind of high energy. And so, for example, let's see how wavelength determines the color/type of light. Let's say that this was 750 nanometers. Nanometers is a unit of length. If this wave were 750 nanometers, the color of light you would see would be red. You'd see red light. And then if we take a look at this short wavelength, let's say that this one's 450 nanometers. If you had light that had a wavelength of 450 nanometers, you would see blue light. So you can see blue light is actually higher in energy than red light. So one way to talk about this is wavelength. Another is frequency. And so basically they tell you the same amount of information. They're just inverses of one another. So frequency is the number of cycles per time. And so it gets this Greek V. And so it's per seconds or 1/seconds. So instead of talking about kind of this distance here, we think about this wave as moving forward, and we see how many crests would it pass per second, right? How many crests of these waves would pass per second? And so you can see that something like here, you're going to have a lot more waves hitting per second than something with a long wavelength. So the equation here to go from one to the other is that V equals C over lambda, where this V here is frequency. This C here is the speed of light. So 3.00 times 10 to the 8 meters per second. And then this lambda down here is the wavelength. And wavelength is generally given, if we're talking about visible lights, in nanometers. So one thing I want you to know is that 1 meter equals 10 to the 9th nanometer, right? It's just another unit conversion. And so one thing we can notice here is that these two are inverses of one another. So as wavelength increases, frequency decreases, right? As these waves get longer and longer, less of them pass a certain point per second, and vice versa, right? So as lambda decreases, as wavelength gets shorter, frequency increases. And then we can continue on and say stuff about their energy as well. As wavelength increases, energy decreases, and as wavelength decreases, energy increases, right? So you can see that frequency and energy are directly correlated, while frequency and energy are inversely proportional to wavelength.